Today we're going to talk about molecular motion. What's molecular motion? Molecular motion is the movement or the motion of the molecules that make up an object. Today we're going to focus on the molecules in a liquid. Now, liquid can take up the shape of any container, and it's made up of small molecules, like all matter is made up of molecules. Now, specifically in the terms of molecular motion, we're going to focus on the kinetic energy of those molecules. Recall, kinetic energy is the energy an object has due to its motion. Okay, so when molecules are moving around, they have more or less kinetic energy depending on if they're going more quickly or more slowly. Now, that motion is directly tied to the temperature of an object. A slower moving molecule is going to have a colder temperature. We're going to feel it as having a colder temperature. Okay, a faster moving molecule is going to be felt as having a warmer temperature. So the warmer an object is or feels, the faster the molecules are going to be moving. The colder an object feels, the slower those molecules are going to be moving, which means warm liquids are going to have more kinetic energy in their molecules, and cold liquids are going to have less kinetic energy in their molecules. So, can we prove it? You bet. Let's test it out. Fill a cup with cold water, another cup with room temperature water, and a third cup with hot water. Then take food coloring and put a drop or two of food coloring into each one of those cups. And time it. Let's see, how long does it take that food coloring to completely mix into each one of those jars? Remember that the molecules making up the water in each of those jars are moving based on the temperature. Therefore, molecules in a warmer liquid are going to move faster than the molecules in a colder liquid. Let's take a close-up here. Here we can see our cold water, and the food coloring looks like it is still actively trying to move throughout that water. Whereas our room temperature is halfway mixed, not completely, but our hot water definitely looks like we have a good mixture of the food coloring and the water going on. You can see just so slightly that room temperature is still mixing, and the cold water, it's barely made any progress since we stopped timing it. Let's break down what we did there. We got 3 different cups, and we put temperatures of varying liquids in each cup. We had 1 cup of cold water, 1 cup of room temperature water, and a third cup with hot water. What we changed each time was the temperature of the water, making that our independent variable. What we measured was the time it took for the food coloring to diffuse in the cups. Diffuse is another word for spreading out. What we were actually looking at was the time it took for the food coloring to completely mix with the water. So our dependent variable is the time it took to diffuse, or the time it took for the food coloring and the water to mix. Now, I did keep a couple things constant during that mini lab. One of them was the amount of water that I put in each jar, and the second was the number of drops of food coloring that I used for each cup. I made sure to time the diffusion of the food coloring in the water. I measured about 35 seconds. That food coloring was completely mixed with the hot water, and it was about a minute 5 seconds or so, and I called the room temperature water completely diffused. That food coloring had mixed in with the water. Now, the cold water, I got tired of waiting for, so I don't know the exact number, but what I do know is it definitely took the longest for the food coloring to mix with the water in the cold cup. And what I do know is the hot water had the lowest time to diffusion. So, did we prove what we were talking about earlier? Did the molecules in the cup of hot water mix the food coloring in faster? Absolutely. It only took 35 seconds. And did the molecules in the cold water move slower and thus take the longest time to mix in the food color? That's what I think, because I couldn't even wait for it. It took so long. So, in terms of molecular motion, we can see the relationship between the movement of molecules and the temperature of those molecules. And if we add in some more scientific words here, we can say that the kinetic energy of cold molecules is lower than the kinetic energy of hot molecules, meaning cold molecules move more slowly, hot molecules move more quickly. And that is molecular motion and temperature.